In the last tape, you learned to evaluate determinants. You also discovered one shortcut. You noticed that if the determinant was triangular, then you could evaluate it by simply multiplying along the diagonal. You also noticed that if the determinant had a lot of zeros, by picking the correct row or column, you could greatly reduce your work. And today, we are going to look for ways to create those zeros that would make life easier. We're going to look at the effect of the elementary row operations on determinants. Now you know that we can use the elementary row operations to write a matrix in reduced form, reduced echelon form. Now sometimes it may be harder to do that than it would be to do the determinant, but we can do some reduction that would make it much easier to evaluate the determinant. Now let's look at the effects. If row B is obtained from A by interchanging two rows of A, then the determinant of B is equal to the opposite of the determinant of A. So if in an attempt to reduce A to B, you get B by interchanging two rows of A, and you evaluate the determinant of B, then you're going to have to take the opposite of that to get the determinant of A. Now the second property is nice because it doesn't change the value. If B is obtained by adding a multiple of a row of A to another row of A, then the determinant B is equal to the determinant of A. So if B is obtained by adding a multiple of a row of A to another row of A, then the determinant of B is equal to the determinant of A. So we don't have to keep up with what was done so we can multiply to correct it or take the sign. All we have to do is just know it would be the same. If B is obtained from A by multiplying a row of A by a non-zero constant C, then the determinant of B is equal to C times the determinant of A. So if we obtain B from A by multiplying a row of A by a non-zero constant, then the determinant of B is equal to C times the determinant of A. Or, since we would be usually interested in getting the determinant of A, the determinant of A will equal to the determinant of B divided by C, because that's really what we're usually interested in doing. We'll evaluate B to get A. So once we evaluate B, we would have to divide B by C to get the determinant of A. Let's look at an example. Let's evaluate 2, -3, 8, 12, 4, 1, 5, 1, 6, 2, 4, -2, 2, 2, 10, 1. Now this is a 4x4 determinant with no zeros. It would take a long time to evaluate it using the techniques of the last tape, because I could pick any row and I expand it and I'd still be left with 3x3. So after I expanded on one row, I'd be left with 4 3x3s. And then once we got to the 3x3s, we could use the shorter way of doing 3x3s and get done eventually. It would take a long time. maybe we can do some row reductions that would make it easier to deal with. What I'm going to do is to try to put zeros in the first column. So we can start, and in fact I think I'll do them all at the same time. I'm going to multiply row 1 by -2, add to row 2. Then I'm going to multiply row 1 by -3, add to row 3. Then I'm going to multiply row 1 by -1 and add to row 4. So this is going to be A. This will be determinant B. So I'll leave the first row the same, 2, -3, 8, and 12. Now I'm going to multiply row 1 by -2 and add to row 2. -2 times 2 is -4, plus 4 is 0. -2 times -3 is +6. 6 plus 1 is 7. -2 times 8 is -16. -16 plus 5 is -11. -12 times 2 is -24. -24 plus 1 is -23. Now I'm going to multiply row 1 by -3 and add to row 3. 2 times -3 is -6, plus 6 is 0. -3 times -3 is 9. 9 plus 2 is 11. 8 times -3 is -24. -24 plus 4 is -20. 12 times -3 is -36, minus 2 is -38. Now we'll multiply row 1 by -1 and add to row 4. -1 times 2 is -2, plus 2 is 0. -1 times -3 is +3, plus 2 is 5. -1 times 8 is -8, plus 10 is 2. -1 times 12 is -12, plus 1 is -11. Now we know that the determinant of B is the same as the determinant of A. And the reason it's the same, as I used method 2, which was to multiply by constant and add to the row, which left the matrices unchanged. Well, B is much easier to evaluate because I have a whole column of zeros except for the 2. So now to evaluate B, I can expand around the first column. So it would be 2 times -1 to the 1 plus 1 times the minor, which is the determinant with row 1 and column 1 removed. So that's going to leave you with 7, -11, -23, 11, -20, -38, 5, 2, -11. I'm going out to the side and evaluate this and come back. So we have 7, negative 11, negative 23, 11, negative 20, negative 38, 5, 2, negative 11. Now the alternate way we discovered for, or used for evaluating 3 by 3 determinants, we'll simply recopy the first two columns. And then multiply down as we go left to right, multiply up, and remember to switch the signs. Okay, so coming this way, multiplying down, the signs will stay the same. So I need to look at the signs. Negative times negative is positive. 7 times 20 times 11. We're going to get 1540. You can check my work with your calculator. Then a negative times negative is positive. So this is going to be 11 times 38 times 5. 11 times 38 times 5 gives me 2090. And then this one's going to be negative 23 times 11 times 2. So negative 506. Now going back up this way, we have to reverse the signs. So a negative times negative is positive, but it's going to be a negative. And then 5 times 20 is 100, times be negative 2300. Okay, this only have one negative, so positive is negative by reverse the sign, so that would be plus. And 2 times 38 times 7 is 532. And then negative times negative is positive by reverse the sign, it's going to be a minus. And 11 times 11 times 11 is 1331. Now if I take the calculator and add 1540 plus 2090, subtract 506, subtract 2300, plus 532, subtract 1331, I get 25. Now you really should check me with your calculator to make sure that I've done it correctly. But now going back to this one then, we have 2 times negative 1 to the 1 plus 1 will be negative 1 to the first, negative 1 to the second, which is positive 1, times we evaluated this determinant and got 25. So the answer to the problem is 50. So the determinant of 2, negative 3, 8, 12, 4, 1, 5, 1, 6, 2, 4, negative 2, 2, 2, 10, 1 is 50. And by fixing it so that the first column had one non-zero number and all the rest zeros, made it a fairly easy problem. Now you might say, well, why didn't you reduce more? So that maybe change it triangular form. So all you had to do was multiply along the diagonal. Well, in order to multiply by a constant and eliminate 11, I would have had to start using fractions. So in my opinion, it's probably easier just to use the technique for 3 by 3 matrices than it would be to produce the fractions. Now I only gave you the principles for elementary row operations, but the same 3 principles hold for elementary column operations. If I interchange 2 columns of a matrix, then I would reverse the signs of their determinants. If I multiply the entries of one column by a matrix by a constant and add them to a second column in the matrix, I do not change the value of the determinant. If I multiply by constant, then I do change the value, and I have to divide by the constant to make it equal. Let's look at an example. Now, of course, this one is easy to deal with anyway, but with the zeros here and zeros there, it'd be very easy to deal with. We could expand along the third row, so it would be 1 times -1 to the 3 plus 1 times the minor, which is going to be row 3, column 1 removed, so that would leave me with 3, 6, 2, 0. Now 3 plus 1 is 4. -1 to the fourth is +1, so that's going to be 1 times 3 times 0, 0, minus 12, which is -12. But now by interchanging columns, I can create a triangular matrix. I can interchange columns 1 and 3, and I can write it as 6, 0, 0, 3, 2, 0, -2, 5, 1. So we interchange the columns. But now, of course, when you interchange the columns, then you change the sign of the determinant. Well, if we call this A and this B, then we know that the determinant of B is just the value obtained by multiplying along the diagonal. 6 times 2 is 12, times 1 is 12. Well, since we interchanged two columns, we know that the determinant of A is equal to the opposite of the determinant of B. So the determinant of A is -12. So it wasn't a lot easier than before since we had so many zeros, but probably some. All we had to do was do the interchange and then the multiplying. As you are working with determinants, always be alert to conditions that will cause a zero determinant. Always be alert to conditions that will cause a zero determinant. One condition is an entire row or column of zeros. So obviously if you have an entire row or column of zeros, the determinant is going to be 0 because you would expand around that row or column, and 0 times the cofactors would always give the 0. If you have two rows or columns that are equal, well, if you have two rows or columns that are equal, then by row or column reduction you can simply add the two, and then that would or multiply one of them by -1, add to the other, and that would introduce your row or column of zeros. So by 1 you would have a 0 determinant. One row or column is the multiple of another row or column, but that's about the same as here. If one's a multiple of the other, then multiply by the appropriate constant and add them, you would get the zeros. But those are the things you can look for to see if you might have a 0 determinant. Example, if A weight 4, 0, 8, 1, 2, 10, 12, 0, 24. Well, I can notice that row 3 is a multiple of row 1. 4 times 3 is 12. 0 times 3 is 0. 8 times 3 is 24. So all I would do is multiply row 1 by 3 so to get row 3. So row 3 is a multiple of row 1. So therefore, the determinant is 0. So always be aware of the 3 factors that can create a 0 determinant.